Okay, and let's welcome the Anthony from the University of Queensland and give us the talk about the superintegrability systems separating in Cartesian coordinates. Welcome, Anthony.
Thank you, CE. Alrighty, so we've we've had discussed superintegrability today in a variety of contexts with the talks of Sam and Victor on coalgebra, um, coalgebraic coalgebraizations. Here, I'm just going to sort of go back to the basics with regards to Hamiltonian systems in two dimensions. So here we're considering a just basic most basic sort of integrability where because there's no time dependence on the potential, all we have to have for the model to be integrable is just one more uh, conserved quantity. And we know that from Liouville's theorem, that means that uh, the the dynamical problem is the Hamilton-Jacobi equation is solvable by quadratures. And if we have um, an additional conserved quantity, that means that we can have an algebraic parameterization of the trajectory. So that's in the classical context, and in the quantum context, we look at superintegrable systems because they display a lot of interesting properties like exact solvability and the existence of ladder operators and hidden symmetry algebras. There's not really a proof of these proof of these properties in the same way that you have for classical for, for classical mechanics, but it's sort of observationally, empirically true that these happen for all the examples. So I'm looking at the case of the hang on, I might just full screen, yeah. Um, the case of separability in classical and Cartesian coordinates. So that's when the potential takes on the additive form, um, where you just have the function of one coordinate plus the function of another. And in that case, the individual dimensional components obviously will commute with each other or be in involution. So that means you have two second order integrals. So the system is integrable. You can always integrate the equations. But then we want to look at extra conditions such that there's an additional constant of motion um, so that is super integrable. And so the way that you go about doing this is you start with the general form of an integral being some polynomial in the momenta and an analytic function of the coordinates. When we deal with classical systems purely, we don't have to have this restriction. We can have something that is analytic in the momenta as well. But for quantum mechanics, it's just easier to make this restriction. And so if we ask for it to commute with the Hamiltonian, then we can derive a PDE for the coefficients of the integral. And so the effectively, if you sort of do all the manipulations, effectively you can write it as like a sort of determining equation. So if you look at the left hand side, this is the index here, the first index here is higher than all the other ones. So you can assume from the outset that like you've solved for all of these other coefficients, and then you plug them into the next equation, and then you try and integrate this series of equations to solve for the next set of equations, and then you sort of go down the list and then eventually calculate everything. That's theoretically, obviously, this is a PDE. It's not very straightforward to actually solve this equation. Um, so, um, but it's simple enough to write down. So the so if you try and count all of the the range of the indices may take on, and the number of equations that are actually specified. There's one too many equations uh, that's actually given. So that means that the equations are overdetermined, and there's one extra condition that's basically needs to be satisfied in order for there to be a solution. And if we evaluate this condition, this is called the compatibility equation, and that's the condition on the potential function such that there is actually a solution to this problem. And if this compatibility equation is satisfied, then we can calculate the coefficients uh, uniquely. So um, now see if we've evaluated all of the other coefficients from the previous set of equations, then uh, this will define a partial differential equation in terms of the potential. So if we think about the highest order situation, that highest order terms in the integrals, that's when k equals 0. So all of the right hand side of this equation will be completely 0. So then this just spells out the Killing equation, and the solution of the Killing equation is just the coefficients of Killing tensor of valence n, and so that's just going to be polynomials in the coordinates, and so then that's going to give us, when we evaluate the compatibility equation for the potential, is just going to be some linear partial differential equation in the potential with polynomial coefficients, um, which is fairly tame as far as PDEs go. If we evaluate the next one, then we get a nonlinear partial differential equation in the potential, which has only been calculated in a few different situations. It's quite unwieldy. And as you go along, the degree of nonlinearity continues, and the equations get a lot more complicated. And um, so just doing the direct method is not necessarily effective in performing an analysis or a classification of these sorts of systems. It's just you just continue to evaluate equations that get more complicated as you go along. So just for reference, I'll just sort of state what the sort of equations that we look at. Um, the linear compatibility equations are quite reasonable. So this is the case where we're applied separability, and we can separate everything into a system of four ordinary differential equations in the potential. So you get a system of effectively identical equations in form. Each of these coefficients here are polynomial functions, and for fixed I, they will all be they'll have they're independent of each other, but the corresponding so for the different coordinate for different I, the coefficients will be mixed with each other. So there's no mixing in the individual equations um, for the same coordinate, but for different coordinates there is sort of a mixing that's involved. So if these coefficients are non-zero, then I'll be able to solve for the potential quite easily. It's just going to be some rational function of the coordinates, but there's going to be other equations that need to be satisfied. So that means that there's the question is, what kinds of rational functions am I likely to find? So the quadratic compatibility equations, these look roughly like this, and there's 8 equations all up, 4 for each coordinate, and I've only got 2 up here, but the other 2 are just basically the same, but just with a different set of coefficients. So we've only solved this equation in a few different cases, and yeah, it's not really clear. At least it's not clear to me how to analyze this sort of integral equation. It's quite ghastly. So um, just to the way that we generally proceed is we try to break down the problem according to which of the coefficients zero or non-zero. And this just allows us to organize the different sort of solutions that appear. So if these linear compatibility equations are all that some of the linear compatibility equations are non-zero for each individual coordinate, then we say that the potential is standard. If the coefficients are all zero trivially, then we say that, the only equations that are non-zero are the ones of this form, or some other nonlinear equations, then we say that the potential is standard. Is exotic. So the other situation was standard, and these are the ones that have rational solutions but of very specific type. So at first order, we get the simple harmonic oscillator, uh, or some linear potential. At the second order, we get a simple harmonic oscillator plus inverse quadratic terms, and for third and fourth order, we get sort of more more interesting sorts of rational functions, but nothing really appears classically. These are all sort of the additional rational components all manifest in the quantum setting, but they all will vanish in the classical limit. But yeah, they're all sort of either oscillator types or just sort of rational functions with no polynomial terms at the front, and just involving reciprocal terms. Now, the exotic solutions are a bit more complicated to deal with. So when you try to calculate them, they just come out to nonlinear equations, which sort of have to stand as the definition for the function. So here, this is just an example. If we had if we've got including the Planck's constant, then this equation here is exactly as proportional to the first Penlevet transcendence, so it's a special function that's not reducible in the general case to any elementary functions. But if we take the classical limit, then the derivative terms vanish, and everything just becomes a quadratic equation for the potential. And so we can in this case we can calculate this readily. And that's generally what happens for classical systems, is that the solution is some rational function in terms of the coordinates. So as the this particular case that we've got here, what's interesting about it is that it's the an example where we don't really have any sort of interplay, any sort of um, the coefficients of the individual components of the potential don't have any mixing. They don't really depend on each other at all. They could they're rather the potential components are independent of one another. And even in the more general case where you can have arbitrary radicals, there's you can have any any radical degree that you want, and it doesn't really matter what the other component of the potential, other coordinate is doing. Um, but this is not really the case in the oscillator case, because you have in each of the cases you've got effectively that they have to the quadratic coefficient has to be the same in each case. But for the terms that lack the oscillator term, there's no real mixing of the coefficients. So this idea that I'm sort of only really developing, and I haven't really defined it quite precisely here, is that there's two kinds of combinations, which I just call here briefly a synthesis. So like, these potentials here sort of can be combined in very specific ways. And you see here that like this potential that's involving sort of the third root of unity here can be sort of attached to a multitude of potentials that are of various types, but it can't be attached to any sort of oscillator um, perturbed oscillator potentials. So the what I would sort of conjecture here is that there's effectively only two kinds of potentials that exist in classical in Cartesian superintegrability, and that is well, you have effectively just uh, potentials in the quantum case that have discrete a discrete spectrum, and these are the oscillator type systems. And then you have uh, systems that have a continuous spectrum, and these are the systems where the one dimensional components don't have any coefficients or any mingling, any coupling that occurs between the individual components. So today, just I'm going to just focus on the oscillator type, the types that have discrete spectrum. These are the ones. So we can go through all of um, the general equations and the starting from the communing with the Hamiltonian, we derive a bunch of partial differential equations. But as we go, we're eventually like no matter how good we are at calculating PDEs, eventually we come to a point where we must stop. And so, in order to really obtain a decent theory, we have to try and address this from the one dimensional perspective of how can we generate these potentials from a one dimensional operator algebra. And so in this case, would I say that an oscillator type system is something that a one-dimensional Hamiltonian that emits a ladder operator. And so if we have two one-dimensional Hamiltonians that emit ladder operators together, then those are the systems that are that's a separable system that will be super integrable provided that the step size of the ladder operators are commensurate with each other. So if we, in the classical case, what this, the condition that's is equivalent to saying basically that the equations of motion are reducible uh, to some linear differential equation um, with sinusoidal solutions, and so that's a fairly simple standard dynamics. Now, with the equation that we generate for finding the ladder operators, it's just it works the same way as it does for the coefficients of an integral, but it's just much simpler because there's only one dimension that needs worrying about. And as before, we can just sort of integrate out iteratively for the coefficients of the potential of the ladder operator. And once we plug this form back into the original equation, we will find just a single leftover term, and that will be the compatibility equation for the potential function, and that allows us to determine what Hamiltonian it must be that that admits a ladder operator of a given form, of a given order. So if we ask for a Hamiltonian to admit a first order ladder operator, then it's fairly easy to show that the only possibility is a simple harmonic oscillator. If we ask for it to emit a second order ladder operator, then we'll have a harmonic oscillator with a reciprocal term. If we go for a third order ladder operator, then the the result is something that's a lot more complicated. It involves the fourth Penlevet transcendent, which again is a nonlinear special function. It there's many. So here when we say the Penlevet transcendent, we just mean the general solution to a certain nonlinear differential equation. And but of course, there are many different kinds of solutions to this equation. They can be rational solutions. They can be exponentials. There are error function solutions. There are solutions in terms of parabolic cylinder functions. Bessel functions. As we go along, we get higher order transcendence, and the sequence of equations that leads to these solutions has been analyzed by a couple of authors that deal with Painlevé transcendence. They have been named in the literature Numi Yamada, um, in honor of the way that they proceeded to analyze the fourth Painlevé transcendent in terms of a sequence of Riccati equations. So here I just wanted to focus on the third order case just because that's reasonably complicated to be interesting enough, but also simple enough to actually discuss with everyone. So I want to. So here, this is the general form of what an exotic potential would look like, and we want to try and use it to obtain the standard potentials. So, and that the standard potentials, as we said, have to be rational. So we start off by trying to find the rational solutions of the Painlevé 4, and they're given in terms of two kinds of solutions. They're the well, six kinds technically, but two kinds in terms of the generalized Hermite polynomials and the generalized Okamoto polynomials. And these has different definitions in literature, but here we'll just consider them as the Wronskian determinants of a sequence of Hermite polynomials. So the generalized Hermite polynomials start from an arbitrary point, and then they just increase the index by one, whereas the Okamoto polynomials start from one, or they start from two, or both, and they increase the index by three. And then they've got a bit of a scaling factor here. Now, so these are the general rational solutions. And if I apply them to the formula for the potential, it simplifies to a very, very neat form. And so that you basically get a harmonic oscillator with a rational term in addition. And they differ just pretty much by scaling. And so yeah, there's this gives us all of the rational potentials that would have a third order ladder operator, but they're not necessarily the standard potentials, and they're just special cases of the exotic exotic potentials. So in order to obtain the standard potentials, we have to sort of think about what are the conditions such that the linear compatibility equation is non-zero. And the way that the coefficients are obtained is by looking at the leading order term in the integral, and they effectively the leading order term has to be a Killing tensor, so it's a function of the Killing vectors, the linear momenta and the angular momenta. And if the linear momenta powers are too high, so here the powers of the linear momenta correspond to which set of compatibility equations are active, non-zero. And if we got j equals 2, j equals 3, for example, that would correspond to that coefficient appearing in the quadratic compatibility equations. J equals 4, j equals 5 would be the cubic compatibility equations. J equals 0, j equals 1 corresponds to the linear compatibility equations. So if we can see j equals 0, j equals 1 terms, or k equals 0, k equals 1 terms appearing, that means that there's this integral came out as a solution to the linear compatibility equations, and we have a standard potential. So now if we have two ladder operators of order k and order L, and we take they've got the same step size, so they increase the ladder operator by the same amount, the eigenvalue by the same amount, and we take the adjoint of one of them, then that will give us, and we multiply them together, that will just give us an integral. Now, if that will give us something of order k plus L, and if I took the difference between that and its adjoint, then I would get something that's of order k plus L minus 1. But you can see here that this is not in when I have something of higher order, I don't really get a standard potential because the k minus 1 and l minus 1 um, won't be 0 or 1. So for if k is 3 or above and l is 3 or above, I don't get standard potentials. But on the other hand, if I would say if we had two integrals that had the exact same sort of form, and I took the difference of that, then I'll be able to decrease the order of the integral, but I'll also increase the power of the angular momentum. So if you start from the original form of what a ladder operator looks like, and then just sort of calculate the linear combinations, then you'll get something of this form, roughly. And here you can see that for k equals 3 and k equals 4, you'll get the appropriate form for a standard potential. So what conditions occur for having two different integrals? And those are the situations where these rational functions are solutions to the Penn-Levy equation in two different ways. So the so in this case, where the kinds of standard potentials are the ones that are both arise from Hermite polynomials, generalized Hermite polynomials, and the ones that also arise from generalized Okamoto polynomials. And so, because the generalized Okamoto polynomials had the scaling factor, if that means that they actually have a ladder operator of a different size, as of 3 times the ladder operator of the one that occurs from the generalized Hermite polynomial. And so, using these different ladder operators, we can construct two different sets of integrals, and that gives us the standard model, the standard potentials at third order. So these are exactly the ones that are derived by Ravel. And if so these sorts of systems, what happens when we have two different ladder operators? We it just yes
4 minutes left.
yeah. So that's no, I'll just skip this slide. The sort of symmetry algebra that we get from this sort of system is much more complicated than we would ordinarily expect for a two-dimensional superintegrable system. So here for this particular example, there's at least 7 generators for the symmetry algebra. So the point that I want to illustrate is that effectively quantum superintegrability, even at this very basic two-dimensional situation, can be very subtle and very complicated, and differs in a significant way from classical superintegrability. Um, so yeah, so thank you very much.
Okay, thank you, Anthony. And any question? No question. Okay, thanks, Anthony, again. If we don't have any questions, and let me